The last three sections of Chapter 4 are all pretty much similar things. They're all talking about doing titrations and doing stoichiometry, solution stoichiometry. So even though they have different titles to them, I've decided to combine the last three sections, 4.6, 4.7, and 4.8, in terms of covering them because they all basically are doing the same practice, which is using stoichiometry to determine a process. Now in solutions, the process we use to figure out something about an unknown solution is called titrations. And you see a video clip on the coverage here, and we'll talk about titrations, and we'll do several titration labs as we go through. But if you recall back to Chapter 3, you've seen this diagram minus the two boxes on the top. In the diagram, we started off with grams given. And then we had moles given. And then we had moles wanted. And then we had grams wanted. And we talked about the fact that going from grams to moles, we multiply by 1 over the molar mass. To go from moles given to moles wanted, we multiply by the mole ratio, which is what we want over what we have. And then finally, we talked about going from moles wanted to grams wanted, we multiply by the molar mass of the wanted substance over 1. In solution stoichiometry, we're going to add in a new box, and the new box is another new starting point, another new possible ending point. And that box is going to be molarity in both cases. If we are given a molarity, that gives us another possible starting point. And to go from molarity to moles given, we're simply going to use molarity times volume times liters, which will also have to be given in the problem. We'll get you to moles given. In this box, we're going to put L and V as well because, moles and volume, so liters, moles, and molarity and volume. We'll get this right eventually. So we'll put molarity and volume up there as well. And you're going to use the molarity equation over volume to get there, or over liters to get there. So this process we're going to look at, all these problems we're going to be doing, regardless whether in section 4.5, which they call gravimetric analysis, or 4.6, 4.7, or 4.8, all of them are basically doing the same thing. Regardless what kind of titration you're doing, regardless what kind of solution stoichiometry you're doing, they're all going to be doing the same process. That's why I decided to tie them into one. So let's start by looking at an example. And again, not all the examples you've done or that are in your notes are done on these screens. Some of them I expect you to try to do on your own. The first example, how many moles of water are formed when 25.0 milliliters of 0.100 molar nitric acid solution is completely neutralized by sodium hydroxide? All right, this is an acid-base titration, and in acid-base titration, we're trying to figure out how many moles of water is going to form. So as before, we said the first step of stoichiometry is to balance the equation. In this case, our equation is already balanced. Step 2 then is to write down what we know and what we want to know. We know that we have 0.025 liters of sodium hydroxide. And my advice is to take any volume in milliliters and automatically change it to liters when you write it down, because liters are what you need for the equation. And we know we have 0.100 molar solution of that. We want to know moles of H2O. So looking back at the diagram, we're going to start at molarity given, and we're going to end with moles wanted. So we need to do 3 steps. So the first thing we do is we're going to take our molarity times our volume. So 0.025 times 0.1 gives me 0.0025 moles of NaOH. Now that I know the moles of NaOH, I need to get from moles given to moles wanted, which needs the ratio. The ratio in this case is what I want, 1 for the water, so 1 H2O, over what I have, sodium hydroxide, 1 NaOH, and therefore we would produce 0.0025 moles of H2O. Now obviously if I wanted to find grams of H2O, I could continue on and multiply by the molar mass. But as you can see, solution stoichiometry basically is the same thing. It's just giving us a possible new starting point. Let's look at yet another example. The quantity of chloride in water supply is determined by titrating with silver ions. And this is an oxidation reduction reaction. We're taking silver ions and we're reducing them by chloride ions and making silver chloride compound. All right, so again, we start with how many grams of chloride ions are in a sample of water if 20.2 milliliters of 0.10 molar silver ions is required to react all the chloride in the sample. And you might have another question down here in your notes that says what percent of the solution is chloride. You can ignore that for this sakes because you really haven't been given enough information. And if you don't have that in your notes, then I apologize. Now, what do we know? We have to balance the equation, which is already done. We, from there, take what we're given. We are given that we have 0.0202 liters of silver ions, and we know that they are 0.100 molar concentration. We're trying to find how many grams of chloride ions there would be in this solution. So again, we start with molarity given, except this time we're going to go to grams wanted. All right, so molarity given times volume will give me 0.00202 moles of silver ions. So now that I'm at moles given, looking at your diagram in your notes, we need to go from moles given to moles wanted, which is a 1-to-1 ratio in this case. So 1 mole of chloride for every 1 mole of silver. And that will give us moles of chloride. To get the grams of chloride, then, I simply multiply by the molar mass of chloride. Now, the question always comes up all the time is, chloride ions, are they the same molar mass as chlorine? And the answer is yes, because technically speaking, chlorine atoms that have lost an electron are still relatively the same mass. The bulk of the mass of an atom comes from the protons and neutrons. Electrons really have no effect on the mass. So since it's lost an electron, a chloride ion still has the same mass as the chlorine atom, which would be 35.5 grams per mole. All right, so mathematically now we simply need to take our calculator and take 0.00202 times 35.5, and we get 0.0717 grams of chloride ions. All right, let's look at yet another example. A 20 milliliter sample of sodium hydroxide is analyzed by titration to determine its molarity. 45.7 milliliters of 0.50 molar sulfuric acid solution are required to completely neutralize the solution. All right, so the first thing we have to do is we have to figure out the equation for this reaction. So what am I reacting together? I'm reacting sodium hydroxide and sulfuric acid. So NaOH is reacting with H2SO4. It is a double displacement reaction. Sodium is going to go with sulfate to form sodium sulfate. So since it's an acid to base reaction, that's our salt that's forming. Sodium sulfate, salt. And hydrogen is going to go with hydroxide, which we learned earlier that H plus OH forms HOH, but we write that as H2O. To balance the equation, I need a 2 here and a 2 here. All right, so there's our balanced equation. Now, what do we know? We know we have 0.0200 liters of sodium hydroxide. We know we have 0.0457 liters of sulfuric acid and that it's 0.500 molar. What we want to know is the molarity of this solution. Okay. Now, given what we know, we can only start with this substance because that's what we know the most about. And we're going to find this. Now, what confuses a lot of students is, what about these things? And I hear that a lot is, what about these two substances? What do we do with them? And the answer is nothing, really. In this problem, they're part of the reaction, but they're really not part of the problem. So we can ignore those for the most part. To get the concentration, we're going to start with molarity given. So molarity and volume of sulfuric acid. And we're going to go to molarity of wanted. So we're going to go sort of down, over, and back up in our diagram terms. So looking at your diagram again, follow along. So starting to go from molarity given to moles given, it says to multiply molarity times volume. So 0.0457 liters times 0.500 gives me 0.0457 times 0.5 is 0.02285. And for the sake of this problem, I'm going to carry an extra significant figure throughout the problem. And that's always a good idea anyway. carry extra significant figures throughout, and then round at the end. If you round all the time in the middle, you end up with over-rounding error. All right, so we know moles now of H2SO4. Next, we need to figure out moles of sodium hydroxide. So we need to go from moles given to moles wanted. We will use a mole ratio. What I want over what I have. Here is what I want. Here is what I have. So 2 NaOH for every 1 H2SO4. So moles of H2SO4 cancel out. If I multiply by 2, I go back to 0.0457 moles of NaOH. Now, I know the moles of NaOH. I know the volume of NaOH from the problem given. So to get molarity, we know molarity is moles over liters. So if I take my 0.0457 moles and divide that by 0.0200 liters, I get 0.0457 divided by 0.0200. I get a molarity of 2.29 molar NaOH. So there's another example of calculating or using stoichiometry. This is an acid-base neutralization. All right, let's look at one thing that ties everything together that we've done. It ties limiting reactants, ties all this stuff together into one problem. In this case, a sample of 70.5 milligrams of potassium phosphate is added to 15.0 milliliters of 0.050 molar silver nitrate, resulting in the formation of a precipitate. All right, so let's look at our reaction we have. We have potassium phosphate. K is +1, phosphate is PO4, it's -3. So that's K3PO4 is our reaction. And we're reacting that to Ag, which is +1, NO3, which is -1, so AgNO3. Now, in a double replacement reaction, the silver and potassium are going to switch places. So silver is going to go with phosphate, Ag3, rewrite that, Ag3PO4. And potassium is going to go with nitrate, KNO3. This is going to be our precipitate, and we know that because this is going to be an aqueous solution. This was an aqueous solution, and this was a solid to begin with. Now, we need to balance the equation, so put a 3 here and a 3 here, and our equation is balanced. All right, so the first thing we did is we've written our balanced molecular equation for the reaction. Now, what do we know? We know that we have 0.0705 grams of this, and the silver nitrate, we know we have 0.0150 liters, and we know that it is 0.050 molar solution. All right, what do we want to know? We want to know how many grams of this is going to form. We're calculating theoretical yield of the precipitate. All right, so we're back to what we were in Chapter 3, talking about limiting reactants. Now we have two problems. We have this quantity and we have this quantity, and they both are going to affect the silver phosphate. If you remember back in Chapter 3, what we did when we had multiple quantities is we took each one and we treated them as a separate problem, which is exactly what we're going to do here. We're going to take first our 0.0705 grams of K3PO4. We're going to treat that as one problem and find silver phosphate. And we're also going to take our 0.0150 liters of 0.050 molar, and we're going to treat that as a starting point. All right, so the first one we have to go from grams given to grams wanted. So we need to find the molecular mass. So again, we pull up our calculator to find the molecular mass. Potassium is 39.1, so 39.1 times 3 equals, we'll clear everything, 39.1 times 3 equals 117.3, plus 31 for phosphorus, plus 64 for 4 oxygens gives me a molar mass of 212.3 grams per mole. Ratio of what I want over what I have in this case happens to be 1 to 1. 1 silver phosphate for every 1 K3PO4. Now, to get grams of silver phosphate, again, I multiply by the molecular mass, which I'm going to calculate again. Silver is 107.9, so 3 times 107.9 equals plus 31 for the phosphorus, plus 64 for the oxygens, gives me 418.7 grams per mole. So all I did was simply break down the silver phosphate and figure it out that way. All right. So mathematically then, 0.0705 divided by 212.3 times 418.7 equals 0.013140 grams of Ag3PO4. So what that's saying is if potassium phosphate is a limiting reactant, that's how many grams we would form. Now let's go the other way. If I'm doing my other solution, this time I'm going molarity given, volume given to grams wanted. So I have to start above. So molarity times volume will give me moles. Now, once I multiply that, I need to go from moles wanted, moles given to moles wanted. So my ratio of what I want over what I have. I want Ag3PO4. There's one of those. Over what I have, 3 AgNO3. So the ratio is 3 to 1. There are 3 moles of this for every 1 mole of that. From there, we do the same thing. We multiply by the molar mass of 418.7 per 1 mole. Okay, so mathematically again, we take 0.015 times 0.05. That equals 0.00075. I divide that by 3, and I multiply by 418.7. Space that out. And I get 0.105 grams of Ag3PO4. All right, so since this is the lower number, that is the theoretical yield of silver phosphate that's going to form. That's how much is going to be there. Now the question is, what's the limiting reactant? Well, if you remember, the limiting reactant is the substance that gave you the lower answer. In this case, our substance that gave us the lower answer was the silver nitrate. So AgNO3 is our limiting reactant. All right, so we've looked here at some different examples of solution stoichiometry titration problems, and they're all relatively the same depending on what you're given. It doesn't matter whether it's a oxidation reduction or a gravimetric analysis or whatever it is. They're all using that same step and process. If you have the diagram, the 6-box diagram that we had back in the beginning of this section, and you follow through that the same way you did in Chapter 3, whenever you take what you're given and go from there, it really is the same process, regardless of what you're finding, whether it's acid-base or oxidation reduction or gravimetric analysis.